All right, so this is section 2 of chapter 3. And in the last section, we talked about the definition and the measurement of variables. And in this section, we will talk about how to test, how to evaluate the quality or usefulness of those definitions through what is called the validity and reliability of measurement. All right, so in the last section, we talked about some of the issues with operational definitions, that these are indirect measures of some psychological construct. And because they are indirect measures, they may be flawed in all kinds of ways. They may capture things other than the construct. They may not capture the construct in the correct or appropriate way. So then, how do we evaluate the quality of a measurement procedure? And it turns out there are really two criteria, which are the validity and the reliability of a measurement. Now, validity and reliability are often defined and measured by the consistency of the relationship between two sets of measurements. So we're going to take a slight detour and review what is meant by the idea of a relationship between two variables. All right, so here's a quick primer on the idea of a relationship. What does it mean for there to be a relationship between two variables? So let's imagine you have two variables or two measures, first measure, second measure. Now you can visualize the relationship between them by plotting the data in a scatter plot. Furthermore, you can use what is called a correlation coefficient to quantify the strength of this relationship from strong to weak. And that value can range anywhere from -1 to +1. And the further the value moves away from 0, the stronger the relationship. So a positive correlation, a positive value of the correlation coefficient implies a positive relationship. And the positive relationship is plotted here. And the idea is an increase in one variable corresponds to a similar increase in the other variable. So for example, height and weight would have a positive relationship. The taller you are, the more you weigh. Number of hours spent studying and grade on the exam. The more hours you spend studying, the better you do on the exam, again, on average. Now, if the correlation coefficient is negative, then you have a negative relationship, meaning that an increase in one variable results in a decrease in the other variable. So, for example, the number of homework assignments and the number of hours spent sleeping might have a negative relationship. So the more homework you have, the less time you have to sleep. And sometimes there's no relationship at all. So if you have a correlation coefficient close to 0, that would be no consistent relationship. And so again, there is a relationship between two measures or two variables if knowing the value on one of these dimensions, on one variable, allows you to predict the value on the other dimension or the other variable. All right, so with those ideas in mind about relationships and what they mean, let's begin by defining the first of the two criteria, that being validity. So a measurement is said to be valid if it accurately measures the thing that it claims to measure. You probably want that to be the case. So for example, does IQ actually measure intelligence? If so, it is a valid measure. Does a personality test actually measure traits like extroversion, um, openness to experience, conscientiousness, etc.? If so, it is a valid measure. Does a thermometer actually measure temperature? If so, it is a valid measure. So we're going to talk about 6 different types of validity, which are face validity, concurrent validity, predictive validity, construct validity, convergent validity, and divergent validity. Okay, so beginning with face validity. Face validity is whether a measure superficially appears to measure what it claims to measure. So is it measuring the right thing on its face? So for example, an IQ test will have questions about logic and reasoning which appear to correspond to the dimensions of intelligence, to the things that we mean when we say intelligence. However, there are some limitations to face validity. For example, it often requires subjective judgment regarding what is or isn't relevant for a particular measure. And also, a test with a high degree of face validity will usually make it obvious what is being tested, what is being measured, and in some situations, you may not want to disclose that. So for example, a job satisfaction survey that directly asks you, how satisfied are you with your job, will have high face validity. But also, people taking the survey will realize immediately what the survey is about. And when somebody knows the purpose of a test or a survey or a questionnaire, it might change how they respond to those questions, and maybe in some cases they answer less authentically. All right, so next we have concurrent validity. And concurrent validity involves showing that scores from a new measurement correlate with scores from an established measurement of the same variable. So for example, let's say you come up with some new test of intelligence. You want to show that it correlates with existing and established measures of intelligence. So in other words, people who score high on your test should also score high on existing, well-established tests of intelligence. So that relationship is being plotted here in this graph. So let's say this is your new measure on the x-axis, and this is an established measure. So ideally, in order to demonstrate high concurrent validity, if somebody scores high on your measure of, let's say, intelligence, they should also score high on the established measure. And if somebody scores low on your measure, they should also score low on the established measure. And a strong positive correlation would be evidence of high concurrent validity. Now, there are limitations here, okay? Just because two measures are related doesn't necessarily mean that they're measuring the same thing. So for example, let's say it's the case that people who have high intelligence also have high self-esteem. And so maybe your test is actually measuring self-esteem, not intelligence. But because these two variables are correlated, your test will show high concurrent validity. All right, so next we have predictive validity, which measures how well a test predicts the specific behaviors that are thought to be related to the measured construct, the behaviors that are thought to be affected by the measured construct. So here's an example. There's something called the Student Risk Screening Scale, the SRSS, and the goal of this scale is to identify high-risk youth. So students who are at risk for various kinds of behavioral problems. Okay, so let's imagine a student takes this test, this scale, and gets some number. And some students get a high number, which indicates that they're at high risk. And some students get a low number, which indicates that they are at low risk. But you can ask, does this number actually mean anything? Just because you took a test and got a number doesn't automatically mean that this number has any meaning or value, especially related to what you care about. So, if this is a meaningful measurement, especially in the realm of behavioral problems for students, then knowing this number should allow you to make predictions about which students will exhibit behavioral problems and which will not. And sure enough, the SRSS is a predictor of self-control and academic performance and the number of disciplinary referrals. So here's a hypothetical relationship that you might see between the SRSS score on the x-axis and the number of disciplinary referrals. And so the presence of a positive correlation would be evidence of predictive validity. You can use the value from this measure, from this scale, to make predictions, accurate predictions about behaviors exhibited by these students. That's an example of predictive validity. Okay, so construct validity determines if a measurement truly reflects the theoretical construct that it attempts to measure. Now, in order to establish construct validity, you have to begin by examining the past research and looking at everything that we know about this particular variable. Then you have to demonstrate that your measurement aligns with the known behaviors and known influences of the variable. So to say that a measurement procedure has construct validity is to say that it behaves in accordance with everything that we know about that construct. Therefore, this is the most rigorous form of validity. It gives us the most confidence that we are actually measuring what we think we are measuring. And lastly, we have convergent and divergent validity. So convergent validity involves using two different methods to measure the same construct, and you want to show that both methods yield scores that are closely related, indicating that they are measuring the same construct. By contrast, divergent validity is when you demonstrate that the measurement is specific to one construct, the construct that you care about, and doesn't overlap with other conceptually different constructs. And this is done by showing that there's little or no correlation between scores of two different distinct constructs. Here's an example of convergent and divergent validity. So there's something called the Relationship Quality Interview, the RQI, and this is used to measure relationship quality. And this is done across 5 domains of relationship quality: emotional intimacy, sexual relationship, support, power sharing, and problem solving. So in this case, convergent validity has been demonstrated by showing strong correlations between these 5 dimensions or domains: emotional intimacy, sexual intimacy, support, power sharing, and problem solving. And because you have a strong correlation between these 5 domains, it implies that they're all converging and measuring the same construct. Conversely, to establish divergent validity, it was shown that the RQI scores do not correlate or correlate weakly to measures of relationship satisfaction. Because satisfaction and quality are considered 2 different constructs. You can be satisfied with a really crappy relationship of low quality, and some people find themselves in that position. And so the fact that the RQI does not correlate with distinct constructs is a measure of divergent validity, and the fact that the 5 domains of the RQI correlate with each other is a measure of convergent validity. Okay, so we talked about validity, and now let's talk about the other criterion, which is reliability. Is your test reliable? And by that we mean the following. Does a measure produce similar results when used repeatedly under similar conditions? So if you take the same test multiple times, do you get similar scores? If the answer is yes, if you get similar scores, then that is a highly reliable test. If the answer is no, the scores are all over the place, then that is not a reliable test or not a reliable measure. Now, reliability does assume that the concept or construct being measured is something constant and something stable. For example, IQ probably doesn't fluctuate very much throughout the week. It's probably pretty stable. Or personality traits. If you are introverted, okay, that probably doesn't fluctuate throughout the week. It remains fairly stable. So for example, again, let's say you take an IQ test, and let's say you take that test 6 different times. And let's imagine these are your results, okay? And let's say they all cluster pretty much around the same value. They're all very close to 115, okay? There's a bit of deviation. Maybe there's 116, 114, but most of it is around 115. This would be an example of high reliability. You have a lot of consistency between the results of different tests. Well, the same test being taken multiple times. Now, conversely, let's imagine you take this IQ test maybe 6 different times, and these are your results. So on Monday, you're at an 85. On Tuesday, you're at 130. On Wednesday, you're at 103. Okay, it's all over the place. This would be an example of low reliability if this were to happen. So again, reliability is the consistency of the outcome of your measure or test over time. And something which produces similar results over different testing periods, different tests, is highly reliable, and something that is all over the place would have low reliability. So every time that you take some measurement, that measurement will contain some degree of error. And error is defined as any other factor that can impact your measurement other than what is being measured. And there could be many, many sources of error. So the measured score can be thought of as a combination of the true score the actual thing being measured plus the error. Okay. Now, if you have high error, you will have low reliability measures. And if you have low error, then you will have high reliability measures. Now, error comes in many varieties and from many sources. So let's talk about some of the sources from which error can come. All right, so let's talk about some sources of error and why the results of a test may be different from one time point to another. So for example, there may be observer errors. The individual who makes a measurement, if a person is making a measurement, that person can introduce error. For example, a professor grading an essay might give the same essay a B plus on on Wednesday, but an A minus on Friday. Okay, there's human error and variability in the ways that humans analyze the world around them, even for the same stimulus. Environmental changes. So changes that can take place in the environment between the two tests. So maybe you take a test on Monday and then the same test on Friday. And maybe the lighting in the room is a bit different. Maybe the temperature in the room is a bit different. Maybe on Friday there's a thunderstorm outside and you can hear it and it's distracting. Okay? So differences in the environment, even subtle ones, could potentially affect your behavior and cause you to perform a little bit different on the same test or the same measure. And finally, participant changes. Okay? So the person taking the same test multiple times may be in a different state of mind. Again, if you take the same test on Monday than Friday, maybe Monday you're more stressed, maybe Friday you're more sleep deprived, maybe one of the days you're more anxious, maybe one of the days you're hungrier. And all of these differences within the individual can also result in variable performance across different time points. All right, let's talk about some ways of measuring reliability. And one common approach is called successive measurements. Now, we've alluded to this in the past few slides. And the idea of successive measurements is that you compare the outcomes of a measure in the same individual at different time points. So again, you take successive measurements. Now, this is often called test-retest reliability. And again, you're comparing two scores of successive measurements of the same individuals, and then you correlate the scores. So again, if we use IQ as our example, imagine you take a group of people and you give them an IQ test on Monday, then another one on Friday, and you just correlate those two scores. And if you have a high correlation between the two testing sessions, that would be high test-retest reliability. Now, sometimes you use the same exact test at both measurements, or sometimes you can use a slightly different version of the same test, which is called parallel forms reliability. All right, next we have simultaneous measurements. And this is often used when you have humans conducting the measurements. So, for example, let's say you're a developmental psychologist and you're examining kids in a playground, maybe a videotape of kids in a playground. And you're trying to count the instances of bullying. Okay, how many times do you observe bullying behavior? So in that situation, you have to operationalize bullying. What specifically are you looking for? And then you might have two different observers both watch the same tape and see if they agree in terms of what is bullying and what isn't. And if you have agreement between two observers who record the same measurements or behaviors, that is called inter-rater reliability. And finally, we have internal consistency, which refers to the consistency across different items within a single test that measures the same construct. And so here, what you're doing is you're ensuring that a test is basically stable or consistent across different components. And the way this is measured is called split half reliability. And the idea is you take a test and you split it in half and you correlate the scores from both halves. So imagine you take an exam in class, 50 questions. And split half reliability would imply splitting that exam into two 25 question exams and see how similar your scores are across those two subsections. And if there's a high degree of convergence between the two sections, that would be an example of high split half reliability. All right, so in terms of the relationship between reliability and validity, these two methods for evaluating the quality of a measurement, we can say the following. First of all, reliability is a prerequisite for validity. So if you think about it, if a measure is not reliable, if your IQ test is giving you drastically different results across multiple days of the week, it's probably not valid. It's probably not measuring actual intelligence or anything remotely similar. So reliability is a prerequisite for validity. If your measure is not reliable, it is also not valid. And so something that is reliable, on the other hand, does not guarantee that it's valid. Even if you have an IQ test that gives you exactly the same outcome each time you take the test, it's not a guarantee that you're actually measuring intelligence. You might be measuring any number of other things using that measure. So I like this little schematic here, which illustrates, hopefully in an intuitive way, the difference between reliability and validity in the form of a target and a bullseye here. Okay, so the bullseye, the target, would be something that is valid, right? And the distribution of measurements would correspond to reliability, distribution of shots in this case, not measurements. So here's an example of something that's reliable. You have all of the shots clustered together, but not valid. It's off target. Okay, so reliable, but not valid. Here's an example of something that's low validity and low reliability. It's off the target, and it's also not reliable. You have the shots scattered all across the target. Here is another example of something that's not reliable and not valid. And finally, here's an example of something that is both reliable. You have a clustering of the shots in the same location, and also valid, you are hitting the bullseye. So again, hopefully this gives you an intuitive sort of understanding of these two really important concepts.